However, let's actually get into experimental evidence. This is just a thought experiment. Let's talk about the first experiment, which made people go, oh, wait a second, Einstein was not full of it. So in 1905, he comes out with this. 1915, he comes out with the math behind general relativity. 1919 was the first experimental evidence for general relativity. Special relativity, still 1905 to actually by the time Einstein won his Nobel Prize, 15 years had passed, and still no evidence for special relativity. 1941 was the first experiment. It's the Rossi-Hall experiment. All right, so the stats, they actually did the experiment in 1940. It was published in 41. So they were looking at muon decay. So muons are tiny little particles that have a shelf life. They have a half-life. They have an average lifetime. The muon, symboled by a mu. Now, traditionally, you put a plus sign there to represent the muon. There are negative muons also, which would be a mu with a negative sign. Clever the way they did that. The mass of the muon is about 207 times the mass of an electron. Here we go, mean lifetime. The mean lifetime is 2.197 times 10 to the negative 6 seconds. So I've had a bunch of muons sitting here on the table. In a little more than 2 microseconds, half of them would be gone. When they go, they decay. And so the muon decays into, there we go. The positive will decay into a positron plus an electron neutrino plus an anti-muon neutrino. Those specs are not of particular importance there. But the deal is, these are charged particles, and if you expose them to a magnetic field, they will curve. Charged particle through a magnetic field curve. We've talked about that. Because the mass is 207 times more than that, that radius of curvature should be a lot greater. The smaller the mass, the tighter the curve. And so we can distinguish between electrons and muons. So you set up these cloud chambers, and basically when you have ions going through it, it will excite the stuff in the cloud chamber, and you'll see a trail. So you can actually see these things. A couple of years ago, the former high school chemistry teacher here actually built a cloud chamber. This requires airtight enough environment, like a fish tank, I think. A radioactive source, and probably ice, I believe. Eventually, cloud chambers would be replaced by bubble chambers, where you take these superheated liquids that are just on the verge of boiling, but you keep them stable, and then the slightest bit of disturbance will cause them to boil. And they boil locally, so you see these little bubbles in the chambers, and you can see which way the particles are moving based upon the size of the bubbles. The bigger the bubble, the longer ago it was. So you would see in the bubble chamber, you would see things like that. You know that it's traveling in that direction. So they go up to the top of a mountain, and they look at they set up the cloud chamber, and they see how many muons are going through at the top of this mountain. And they had 563. In 1 hour in this tank, top of a mountain, 563 muons. They went to a lower elevation, so the difference in elevation was 1,907 meters. The speed at which these were traveling, there was some variation, but it basically came out to beta was 0.9952, which is the reason why I had to do that one over there. And so now they're going to predict how many muons should they expect to see down here. The idea was that 563 muons would be pretty standard, that over the course of an hour, no matter what hour they did, it would be roughly that. They might have pinned it down to, during time of day, but they counted them up here, then they counted down here, and made two predictions to see which one came out right. So first prediction, special relativity is bunk. So I am traveling at 0.9952 times the speed of light. So my speed is 0.9952 times the speed of light, which is 0.9952 times 299. Be in here. That's what I always debate of how exact do I get at this point, and I'm feeling in the mood for exact. There we go. I wrote it in here. 299,792,458 meters per second. And so how fast were they traveling? Let's give me some more decimal places than that.
2.98353 times 10 to the negative 8, or positive 8. Or do you want more decimals?
That's probably sufficient for what we're doing here. All right. So about 290, a little more than 298 million meters a second. So if special relativity is bunk, the amount of time it takes for the particles to get from here down to here would be, well, I know that this speed is distance over time. Therefore, the time would be the distance over the speed. And the distance was 1,970 meters divided by that number that you just calculated. $6.31579.
917. I'll restart.
Okay.
6.3917477 times 10 to the negative 6
seconds. Well, if the average lifespan is a little more than 2, this is almost three average lifetimes. So let's calculate. Basically, whenever I'm dealing with decay, I have the basic setup of n is equal to some n sub naught e to the negative, I'll just write alpha t, some coefficient alpha there. So as time gets bigger, this fraction gets smaller, and if you multiply it times the initial number, you get how many should exist. I know that the average lifetime, so that should basically be the average life, so, suddenly I was gonna treat it like a half-life. I don't suppose I have the half-life here, that would be more convenient at the moment. Oh, the half-life, instead of average life. I'm gonna change that number to half-life, 1.56 times 10 to the negative 6 seconds. So I have 1/2 of my original number, e to the negative alpha t. In other words, 1/2 is equal to e to the negative alpha t, or the natural log of 0.5 is equal to negative alpha, oh, I forgot to put in my time there, tau 1/2. Times 1.56 times 10 to the negative 6 seconds.
Four hundred and forty-four thousand.
444,325.
325.
440,329.
444,000. Sorry.
444,
Thank you.
325.
And that'd be, pardon?
Well, I got
That's
that.
negative.
Yeah, it's positive.
Yeah,
Is it
because we
negative?
have a negative sign.
All right, so by this, the number of particles should be whatever I started with, which is 563, times e to the negative 444,325 times time. This is our prediction for the non-relativistic. If relativity is bunk, that's how much time it should take, and so we plug that in for time, and so we get 563 e to the negative 444,325 times 6.39174777 times 10 to the negative 6.
I got 32.89.
32.89.
Yeah.
Confirmation?
I can confirm.
All right. So somewhere around 30, 32, 33 is what you'd expect. You know, there's some error bars in there. All right. Now, if relativity matters. So non-relativity, so relativity, if special relativity is true, how much time passes for the muons? Well, that's the amount of time that passes for us, 6.392 microseconds passes for us. That would be equal to gamma times proper time, from the muon's point of view. And gamma was 10.218. That's what we calculated before, right? So I actually wrote it down. Yeah, 10.218. And so, from the muon's point of view, whatever 6.392 microseconds divided by 10.218, that's the amount of time that passes for the muons.
So 0.625 seconds. Or
0.6
not seconds. 0.625.
0.625 microseconds.
Right.
So now we can make a prediction from the muon's point of view. N is equal to 563 times e to the negative 444,325 times 0.625 times 10 to the negative 6th. And so now we have a prediction here.
$426.
422,
26.
26. So an incredibly huge difference. So relativity is bunk, we should get 32 or 33. Relativity is true, we should get 426. The official number that they had was 420. The first solid piece of evidence that special relativity is true. At this point, it was pretty much believed for the most part, but it's always nice to have evidence. There have been other variations of the experiments all coming out supporting special relativity. There is the next major experiment on special relativity happened in 1971. That is the Keating, the Hafele and Keating experiment. Perhaps one of you can pronounce this name better than I can. Sure, okay.
What is it?
Hafele, oh, sure. There were two physicists who did the experiment. Keating was one of them, and that was the other guy, Hafele.
Is it Middle Eastern, the name?
It always seems like that to me, but I don't know. Where they basically took atomic clocks and got them synchronized down to the billionth of a second. They put one onto a plane, commercial jetliner, which flew basically around the world east, another one that flew around the world west. And, we're not traveling near the speed of light, but we are traveling to the point where the time, we should see time dilations down to at least a billionth of a second. And they actually did come out with evidence. The Western flight was far more accurate. The prediction was that they would be off by, traveling west, 275 nanoseconds was the prediction, plus or minus 21 nanoseconds. That was the prediction. And what they actually got was 273 nanosecond difference. The eastern flight was a little bit farther off, but still within the error bars. The flight east, the prediction was negative 40 plus or minus 23 nanoseconds. And what they got was 59. So plus or minus some error bar there. But within the standard deviation, there was overlap. So this is the evidence that special relativity is true. Let's talk about some of the implications. Questions to hear? So we have this gamma is equal to 1 over the square root of 1 minus beta squared. And I think we did this before. What happens if you're traveling the speed of light? Or maybe that was a different group. So t is equal to gamma tp. So if the speed is the speed of light, what is gamma?
Approaches infinity. Approaches infinity.
It does. It becomes hugely, becomes large. Well, actually, it would be infinitely large if v was equal to c. But talk about the Facebook post and how long it would take to travel at the speed of light, how long it would take to get to the moon. So somebody posted basically to give some idea of distances, they said if you're traveling the speed of light, you would get to the moon in 1 second, get to the sun in 8 minutes, and there were various things like that. And I said, if we were actually traveling the speed of light, yeah, 1 minute might pass for you, but the amount of time that the rest of the universe passes, the amount of time for the rest of the universe is infinitely large. So by the time you got to the moon, it wouldn't be there. It would have disintegrated into its base particles. Then I threw in isn't relativity fun? So, because we get a 0 in the denominator, the math people still haven't figured out how to do that. And so, if you get a 0 in the denominator, 0 in the denominator, beta is equal to 1, it's bad news. And it turns out, with further theory, that in order to go the speed of light, you have to be a massless particle. Anything with mass can never go the speed of light because the math says you can't do it. So therefore, as we get particles, if we put more and more energy into particles, those particles will get closer to the speed of light. Well, in classical physics, as I put more and more energy into it, the particles should just keep getting faster and faster. But what seems to happen is it will get closer and closer, but we'll never actually hit it. Why? If I apply a force to an object, it has a set acceleration. Theoretically, if I can keep applying the same force, isn't the acceleration eventually going to take it past the speed of light? Obviously not, but what happens? Let's say that I could apply the same force to an object forever. Newton's law says F equals ma. So if that's constant, or is it? This actually won't be constant because the mass is not constant. As you get closer and closer to the speed of light, m starts to increase. So if I apply the